Good evening, this is V. Sujit Babu from ECEP section, ECEC section. Today my topic is about soil erosion control using electric fields from electromagnetic wave equation and transmission lines. So let's look onto the introduction to soil erosion and its impact. Soil erosion is the gradual removal of topsoil by wind, water and or human activity, leading to reduced agricultural productivity. It causes land degradation, sedimentation in waterways, and loss of fertile soil critical for food security. Conventional control methods include terracing, vegetation cover, and mulching, but they may be costly or environmentally ineffective. Emerging technologies like electric field-based stabilization offer non-invasive, energy-efficient alternatives. This presentation explores how controlled electric fields can migrate the soil, practical displacement, and at the microscale, electromagnetic principles relevant to soil particles often carry surface charge due to ion exchange and mineral composition, making them responsive to electric fields. When an extremely electric field is applied, charged particles experience Coulomb forces that can bind them together. The electric field equal to V by D relates via voltage V across a distance D, determining the strength of a particle interaction. This principle leverages electrokinetics and movement of charged particles in response to electric fields already used in decontamination. Understanding permittivity and conductivity of soil helps predict how effectively it transmits electric fields. Electrokinetic phenomenon in porous media. Electroosmosis derives fluid flow through soil pores when an electric field is applied, aiding in moisture redistribution. Electrophosphorus causes movement of charged colloidal particles, potentially clustering fine slit and clay near electrodes. This phenomenon can reduce pore water pressure and increase interparticular cohesion, enhancing soil stability. The zeta potential, a measure of particle surfaces charges, determines water increase. Colloidal particles potentially clustering fine steel and clay. This phenomenon can reduce and the jet can be determines the magnitude of electrode response. Electrode response, low frequency AC or DC fields are typically used to avoid electrolysis, unwanted chemicals, unwanted chemical reactions in soil. Mechanism of electric fields. An applied electric field induced soil stabilization. An applied electric field polarizes soil particles, inducing the dipole moment that promotes particles alignment and aggregation. Cations in pore water migrate towards the cathode, forming a folliculated structure that bind line particles together. This process increases shear strengthening and reduces erodibility without adding chemical binders. The effect is most pronounced in fine-grained soils like clays due to their high surface charge density. Fine strength and duration must be optimized to avoid overtime dyeing or electrocorrosion. Key parameters influencing effectiveness. Soil type significantly affects performance. Clay-rich soils respond better than sandy ones due to higher ion exchange capacity. Moisture content must be sufficient to allow ion mobility but not so high as to cause short circuiting. Applied voltage typically 10 to 50 volts DC and electrode spacing determines the field uniformly and penetration depth. The treatment time ranges from hours to days depending on soil resistivity and desired stability level. Temperature influences ionic mobility with warmer soil generally showing faster electrokinetic response. Mathematical modeling of electric field distribution, electric potential psi in soil follows Laplace equations. Del square psi is equals to 0 assuming steady state and a homogeneous conditions. This allows the prediction of voltage distribution between electrodes using boundary value methods. Current density J equals to sigma E links conductivity sigma and electric field E, helping estimate power requirements. Finite element stimulates can model complex geometrics and heterogeneous soil layers accurately. Accurate modeling ensures uniform field application and prevents localized over treatment or failure zones. Electrode design and placement strategies. Electrodes are typically made up of inherent materials like graphite or stainless steel to resist corrosion in most soils. Vertical placements along slope contours help stabilization enter soil profiles against sheet erosional ridge beneath the surface can protect against surface level flow and piping erosion. Spacing between anodes and cathode ranges from 0.2 to 0.5 to 2 meters, optimized based on soil resistivity. Periodic periodic polarity reveals in AC mode can reduce electrofluidic folic and improve long-term performance. Experimental validation and field trials. Lab scale tests shows up to 60% reduction in erosion rates after 48 hours of low voltage DC treatments. Field trials on highway embankments demonstrated improves vegetation establishment due to stabilized topsoil. Topsoil monitoring includes measures of soil shear strength and moisture content, electrical conductivity pre and post treatment. Non-invasive sensors like ground penetrating radar cells access the subsurface changes without disturbing the soil. Result confirm that electric field treatment is most effective when combined with initial seeding or mulching. Advantages over traditional erosion control methods. Electric field methods require no excavation or heavy machinery, reducing environmental disturbance. They consume minimal energy, often powered by solar panels, making them sustainable for remote areas. No chemical additives are introduced, preserving soil biology and groundwater quality. The treatment is reversible and adjustable, allowing fine tuning based on seasonal or climatic changes. Long term maintenance is low once electrode are installed and automated control systems are in place. Challenges and limitations. Highly conductivity or salination soils may short circuit the system, reducing efficiency, and energy consumption increases with soil resistivity, making and or clay heavy soils more costly to treat. Electrode degradation over the time requires periodic inspection and replacement. Large scale deployment needs a robust power management and remote monitoring infrastructure. Public perception and regulatory approval may pose hurdles due to unfamiliarity with electromagnetic soil treatments. Integration with smart agriculture systems. Soil erosion contents via electric fields can be integrated into IoT enabled precision agriculture platforms. Sensors monitor soil moisture, erosion risk, and field strength, triggering treatment only when needed. Machine learning models can predict optimal voltage and timing based on weather forecasts and soil data. Solar powered microgrids make them the system viable into off-grid rural region prone to erosion. Such integration supports sustainable land management under climate change pressures. Future research and directions. Investing pulsed electric fields to enhance practical aggregation while minimizing energy use, developing biodegradable or self-healing electrode minerals for long-term deployment, studying long-term analogical impacts on soil microbiota and plant root development, scaling up plot projects over to watershed level applications with modular electrode arrays, exploring hybrid system controlling, combining electric fields with biochar or microbial stabilization for synchronistic effects, conclusion and engineering perspectives. Electric field based based soil erosion control leverages fundamental electromagnetics to address an environmental engineering challenge. It demonstrated how transmission lines and field theory concepts apply beyond communication systems to ecological sustainability. While not a standalone solution, it is complements the traditional methods with precision, scalability, and low environment impact. Electronics and communication engineering plays a clear role in designing control circuits and sensors and power systems for such appliances. The the interdisciplinary approach highlights the expanding role of EC in environmental and civil infrastructure innovation. Thank you.